We have a question in the chat from Ichi again to Josh, which is how much difference do different methods have when dating the same rock or crystal? And I'm not sure, is that, Ichi, maybe you would go ahead and unmute. I'm not sure if you're talking about crater counting or if you're talking about radiogenic isotope dating.
Could you hear me?
Yeah.
Oh yeah, I'm talking about isotopic measurements because Vagila and some presenters talk about this, and actually I found that ARL Archean dating is looks much younger than like the PB dating, and I want to know how many difference does different isotopic methods have, and I know Josh is an expert of this field.
Thanks, Yuji. I mean, it gets back to, I guess, the question I was asking Wajia. It's not really a simple answer, but different methods rely on kind of quite, I guess, what we refer to as like different resetting temperatures. So things like argon we know are much more easily reset in the mineral systems that we look at compared to the uranium lead system, for example. And so it could be different events that are causing those ages. So so for example, when Wajir is talking about 2.1 billion year old ages, they're not actually, or they are almost certainly not going to be the formation ages of those basaltic, those creep rich materials. There will be some later event that modified them. But yeah, so it's kind of interesting though. I guess my question to Wajir was all about the fact that, I guess, if you're comparing these different things, you have to always be aware that your decay constants that you use to calculate the ages will constantly kind of get revised, and it's just always good when you're comparing different isotope systems to try and keep those in line as much as possible, so you can have a good idea of what your absolute ages are.
Thank you. Feel free again to raise your hands if you'd like to speak out loud or write a question in the chat. I had a question actually for Lauren, which was, you mentioned ice at the very end of your talk, or the presence of ice. I was wondering both if you've thought about how much ice might change that, I guess, that size threshold that you've described or observed, and also does the size of crater actually tell you something about maybe hazards analysis when we're going to be sending rovers or even humans into some of these PSRs in the future?
So within our research at this point, we have not included anything with regards to strength variations or anything containing water ice. So I just bring that up as like in the future, like in the event, because it would be very integral in looking into that, because it would obviously change the conditions at which you're looking at it. In addition to how much, I guess, what's the word? So in addition to changing the strength conditions, it would also change what the crater populations you would find there are, because it would also alter those as well. So in the future, hopefully.
Well, Jiha, do you see any questions, or do you have a question for anybody in the audience?
Oh, yes. So I do have a question from Edward, and I'm not sure if I missed it or was it there. I didn't see any factor of time in your model. So I was thinking that if you're talking about collapsing, then which model will fit which time range? How long do you expect them to fail? You
mean like how long would I expect them to like stay stable for before failing?
Right.
Okay. I guess I'm sort of, yeah, I didn't really have a time aspect in my models, like it wasn't evolving over time. So I guess I'm just working on the assumption that any lava tube on the moon has been there for so long that any collapse that would likely to occur has already occurred. So I guess I'm not really trying to figure out, and it isn't really evolving with time. It's not, I'm not trying to figure out when things would collapse, just like if they would collapse or not, I guess.
Go on.
Yeah, sure. I was thinking in a way that if you talk about these lava tubes, you're more concerned about that could be habitable in future, and that's where the stability ideas comes from, I guess, or?
Yeah, I was thinking the stability idea for like, I was thinking the impact of stability on habitation would be more like, not like if it was going to collapse while people are inside it, but just like if it's collapsed at some point in the past, if it would have left like chunks of debris on the floor or cracks that would make the floor difficult to use or anything like that. So I'm sort of assuming that any collapse has already happened, and I'm just trying to figure out how much damage that collapse has caused, I guess.
Okay.
Did that answer your question?
Yes, thank you.
Yeah, thanks. Thanks for the question.
And then I actually had a follow-up, I guess, which is I noticed in your talk, or you made a point in your talk that you have tensile fractures or tensile failure at the bottoms of some of these large tubes. And I'm wondering, is there a threshold of tube size that you see where, at a certain meter diameter smaller tube, we can go in and expect maybe a pristine floor, whether or not it's piled on with roof collapse, but a pristine floor?
Yeah, I think so. I mean, for the ranges of size that I used, all but one of them had tensile floor failure, but I think it was the very smallest and narrowest of them didn't have any floor failure. It was, I think, 500 meters wide and a roof thickness of 50 meters. And that was the only one that didn't have any failure on the floor. So I haven't yet, but I might do some more test models of just like a very small sizes and very small roof thickness like that to see if models that are that small also don't have any floor failure.
Thank you.
If anybody has a question, they can also raise hand and ask directly.
So as we're waiting for fervent questions to roll in, I'll just one more time tell everyone to meet in the GatherTown Conference Room 1. We're number 1. To just mingle with other geologists for our sort of session networking event. And that will happen at the top of the hour in whichever time zone you're in, again, except for Newfoundland. All right, we have Toshi Hirabayashi has asked Catherine regarding landslide, or has given an answer to Catherine, which I think you could find in the chat.
If you would like to discuss it, you can turn on your microphone. And
yeah. So this is Toshi. So I was working with Lauren. So regarding question from Catherine, I added some comment on that. Basically, we observed smaller craters, or technically like smaller than 700 to 800 meter diameters than larger craters. So our interpretation was that so smaller craters can exist on the slope, but larger craters cannot. So our interpretation was that because of this, larger craters can bring higher kinetic energy to fragment the surface, the slope, but the smaller ones cannot. So because of this, we considered enhanced landing enhanced landslides will be the key contributors to degrading surface slope. This is what we are thinking.
Thank you for that explanation. Samuel, I think you have your hand raised.
Yeah, I've got a quick question for Marissa about the modeling, if she's still around. Yeah. Do these models pertain to a particular size range of lava, of ascension? Is there a particular size that these are particularly applicable to?
Yeah, so it's modeling magma rising within, you can set the diameter of the dike. So it is assuming like a more circular or oval shaped dike rather than, as we know, they're probably more sheet-like in reality. So yeah, I mostly based the sizes of it. Well, there are some measurements for like lunar dikes, which are based on like satellite measurements, you know, sort of the gravitational anomalies that you can get. But the detection limits on those are for like kilometer scale dikes rather than like meter scale ones, which were the ones that I was picturing. So I sort of went for a bit of an in-between between these geophysical measurements and like dike surveys on Earth. So yeah, that is something that you can play around with in the model.
Does it make a massive difference on the dynamics if you change it significantly?
Yeah, so based on that sensitivity analysis, the main thing I was seeing is that it was affecting like the mass flow rate. And yeah, it has a really strong control on that. So yeah, it's a difficult one to constrain that does have a big effect on some of the results. So yeah, I think some of the things I'm hoping to do in future are to take some of the outputs from the magma ascent model and put it into some sort of eruption model. And it might be at that stage that I sort of have a play around with that conduit radius and see, you know, what sort of different eruptions that could produce.
Cool, thank you.
Marissa, do you have an event eruption model in mind?
So I've been looking at a couple of different ones. So there's a terrestrial model called EJECT, which is mostly used for like probabilistic studies, thinking about like mapping out hazard zones around different volcanoes. But it's quite useful for just seeing, for comparing with say like just different satellite images we have of like the furthest extent that the different pyroclasts could go to. So yeah, just something, quite a simple like ballistic ejection model would probably be suitable, especially because, yeah, I'd probably assume that there isn't too much of an atmosphere present when the eruption is taking place.
That'll be very exciting to see.
Yes, yeah, hopefully I'll have time to do that during my PhD.
Well, I think that if there aren't any other questions, I think that we can give everyone about a 15-minute break before they move on to their network session of choice. But again, our network session is in room 1 in the conference rooms at Gather Town. Do you have any final thoughts, Vijaya?
No, I would also like to say thank you very much to all speakers and everybody who participated in this discussion. Thanks a lot and have a nice rest of this conference.
Yeah, and thank you again to Ashkan for our excellent IT support as well.
Yes.